A sensor provides an output that corresponds to changes or events that you might have in your environment. And a sensor, I want to be very clear about the definition between a sensor, the distinction between a sensor and a transducer. So a transducer, in contrast, and a sensor is a transducer. A transducer converts energy from one form to another. So transducers can also be actuators. I take an electrical input, for example, and I output some action on the world, whereas a sensor is often taking a signal from the environment, a pressure, a force, a temperature, and converting that to, for example, an electrical or an optical signal. So a more graphical depiction of this might be if you have an environment with some measurand, and the measurand is a physical signal that the sensor will detect. So that might be something like light, or temperature, or pressure, or sound. Any of those things could be a measurand. All right, but we don't just stop at the sensor, right? Often what we're going to do is connect that sensor to some interface electronics. And those interface electronics might do things like amplify or filter the signal so that we can more easily detect the parts of the signal that we're interested in. And finally, you might go from those interface electronics to something like an ADC or microcontroller like you have on your Arduino, so that you can digitally capture the data that you have from your sensor, and so you can analyze that on your PC, for example, or use that in some other kind of control loop. Okay, so that's the basic pathway that we might have in a sensor setup. And we obviously have various signals throughout here as well. So we have the measurand, and that's a physical signal. So that could be something like a light, a temperature, or pressure. The output from my sensor itself might be something like a resistance, it might be a capacitance, it might be a voltage, right? It could be a number of things that are coming directly out of that sensor. So the thermistor, for example, that you have in your kit will change resistance, and so the output signal directly from that thermistor is a resistance. It's not necessarily a voltage. And so the way you might convert that resistance or capacitance to a voltage is going through the interface electronics. And so the signal that comes out of the interface electronics might be something like a voltage or a current, or something that you could potentially measure on an ADC or a microcontroller. And then, of course, outside of the microcontroller, you could have something like a digital serial signal, you could have a Wi-Fi signal, you can have a lot of different signals coming out of your microcontroller or whatever board you have that's digitally analyzing those signals. Now, a quick example of this kind of signal pathway might be something like the cadmium sulfide light sensor photoresistor that you have in your kit. So this is a CDS light sensor, and based on some change in light intensity here, I'm actually going to see a variable resistance. So a lot like that thermistor, I'm just going to have a resistance that varies based on whatever light intensity is currently on the sensor. So I could go directly from this and create some interface electronics that would get me a signal that I might be able to read on something like an Arduino. Ultimately, I'd be interested in getting a voltage signal. And to do something like that, I could just set this up as a very basic resistor divider, where I have ground on one end, plus 5 volts on the other. This one right here is my cadmium sulfide light sensor, and then I have my output voltage coming out of the middle of this resistor divider. And then finally, I could have this going to the ADC and microcontroller on the Arduino, and if I really wanted to get fancy, I could have a serial signal going from my Arduino to something like processing and display something like 2 lux to give me the light intensity that I'm actually reading from that sensor. So that's a really simple kind of pathway that I might design in order to read a light intensity in the environment. Now, an added complexity to this, I can see if I try to measure something like acceleration. It's really hard to measure acceleration directly. So I might need a couple steps to go from the measurand of interest, in this case acceleration, to what I can actually sense. So in our acceleration example, we might be interested in measuring an acceleration, and that might be in something like meters per second squared. But I can't measure that directly, so I can calculate a force in newtons, right? But maybe I can't even measure that directly. But what I can measure directly is displacement in meters. So I'm measuring a displacement, but then I'm calculating, based on known parameters or maybe calibrated parameters, the actual acceleration that I got that generated that displacement. So an example of a sensor design that might do that, this is the very simple example, is a mass on a spring. Right? So if I apply a force on this mass, right, and my force is related to my acceleration through that mass, and I'm looking at a displacement here of x. I also know that F is kx for the spring here, and those two together, I can calculate my acceleration is going to be kx over m. So x then is ultimately what I'm measuring, right? And k and m I assume are known, or perhaps I calibrate those particular constants. And then, of course, along the same lines, maybe I'm measuring my displacement is giving me a capacitance output, and then I can design some interface electronics to go from a capacitance output to a voltage, to an ADC, to a digital signal. All right, there are obviously a lot of parameters that you might care about if you're actually going about choosing a sensor for a particular application. This is a non-exhaustive list. I know it looks exhaustive. And we'll talk about some of these parameters more in depth, but I just want to give the brief overview of what these parameters mean as far as sensor performance. So sensitivity we often define as K, and sensitivity is going to be our output over our input in our sensor. Right? So if I have an output in resistance and an input in temperature, right, I'm getting units here of ohms per degree C, or ohms per K. If I had an output of volts and an input of pressure, right, I'd be looking at volts per Pascal. So the range of a sensor we're often going to define as, this is the input range, is going to be the maximum input value that the sensor can handle minus the minimum input value that the sensor can handle. This is sometimes given in decibels, but this would be the parameter I'm interested in. For example, if I know that I need to be able to measure 50,000 kilopascals, right, and I only have a sensor that goes from 10 to 4,000, it's going to do me no good. So I need to make sure kind of the range that I'm interested in is covered by the sensor that I pick. All right, accuracy is going to relate to the expected error, right? And this is defined as my measured value minus the true value I have. So if I have a true kind of ground truth temperature of 47 degrees C and my temperature sensor is giving me 47.2, that gives me some sense of the accuracy. If I took that measurement many times, I'd get some sense of the accuracy of my sensor. Right, resolution, you're looking at the minimum signal that the sensor can detect, and typically this is defined based on the noise level you might have in that sensor divided by the sensitivity of the sensor. Noise is going to be everything that shows up in your signal except for the true signal. And obviously there's lots of different types of noise that you might get in your signal as well. So bandwidth, you're looking at how fast I can sense that measurand. So if I need to be able to sample at 100 kilosamples per second, obviously I need a very high bandwidth sensor in order to do that. Things like size and integration are answering the question of does it fit into my my system design. So if I'm trying to design some kind of general mechatronic system and I need this big bulky sensor, or it's really tough to integrate into my system, that might not be the best choice of sensor either. And finally, power. Typically we're interested in just kind of power consumption in watts of what that sensor might draw. So a typical level for something like an inertial sensor would be on the order of milliwatts, maybe tens of milliwatts. A lot of sensors, a lot of the interesting kind of development in sensors has really been pushing them to lower powers than they've been able to achieve in the past. Right, but all of these things you should be able to look up in some sense on, for example, a sensor data sheet, and be able to pull out some of the metrics from that data sheet that you would be interested in if you're trying to design this and integrate this into a system.